Hello, I welcome you all to Impala training sessions. In today's session, I'm going to introduce Impala to you. We'll discuss how Impala differs from Hive. We'll take up the Impala's core components along with the execution architecture, and last but not the least, we are going to discuss about metadata caching. So let's get started. First of all, let's have some introduction to what Impala is. Impala is a general purpose SQL engine developed by Cloudera. Cloudera feel the need to actually bridge the gap where people were using Hive to do querying on Apache Hadoop or the data which is stored on HDFS and the Hadoop ecosystem, and they were having some latency due to the execution of MapReduce jobs. Impala is a real-time query engine. It utilizes the massively parallel processing database engine which is developed by Cloudera. It integrates into the Hadoop stack on the same level as MapReduce, and not a bit as Hive and Peg are. In the diagram, you can see that the bottommost layer that we have is HDFS, which is the Hadoop distributed file system, and on top of it, we have this component which is MapReduce, which actually makes the base for the tools like Peg and Hive. Whenever we write any kind of query or any kind of script in Peg and Hive, it will be translated to map and reduce and will act upon the data which is stored on HDFS. Hive, which is the closest competitor to Impala, uses the same paradigm as well. We'll write some Hive script. That Hive script will be converted to MapReduce program, and that MapReduce program will be executed on the data which is stored on HDFS. The thing is, the conversion into MapReduce and the overhead to start those jobs is actually a lot when we are talking about real-time queries. Impala, if you see in this diagram, sits right next to MapReduce and not something like on top of MapReduce as Hive is. So when we are going to write any queries, we are going to execute any query using the Impala execution engine, it will not leverage the MapReduce processing paradigm, but will rather use the MPP or Massive Parallel Processing Database Engine, as we discussed, which is developed by Cloudera, to process the data which is there in HDFS. What Massive Parallel Processing Database Engine is, we'll discuss about these things in the later slides. As we discussed in the previous slide, Impala is a general purpose SQL query engine. It works very well for both the analytical as well as transactional or single row workloads. Impala supports the queries that takes from milliseconds to hours, as against talking about Hive, which actually takes a bunch of seconds to start up even before it is going to perform a very small operation which will last for milliseconds. Impala runs directly with Hadoop. It reads the widely used Hadoop file formats, for example Avro, Parquet, JSON, flat file format, and other row and columnar data stores, and is able to process them. It talks to the widely used Hadoop storage managers, and it actually runs on the same nodes that run the Hadoop processes. Impala uses the same cluster that the other Hadoop jobs are using, which are notably written in Java MapReduce, Peg or Hive. But please do know that Impala do not use MapReduce at all, as we have discussed in the earlier slides. Impala is a high performing engine which is built in C++ instead of Java. It helps us doing the runtime code generation and is a completely new execution engine, and it do not utilize MapReduce processing paradigm at all, as it has been discussed in the previous slides. Moving further, it provides a fast and interactive SQL queries directly on the data stored on HDFS or HBase. HDFS data is something which is stored in the form of files on the distributed file system, where the files will be divided into blocks, and whenever we are going to execute any query, it will span upon multiple slave nodes which are there, and will perform the execution parallelly and will return the results. On the other hand, HBase is a NoSQL data store which is going to have our data in a columnar storage in the form of row key and column families. Impala can also work on top of it and can actually help us in removing the shortcoming of HBase, which is no SQL, or you can say that no structured query language paradigm which is provided with that. Impala uses the same metadata and the SQL syntax which is used in Hive, the Open Database Connector drivers, or commonly known as ODBC drivers, and the user interface, for example the Cloudera, Impala UI and Hue as Apache Hive. This provides a very familiar and unified platform for real-time or batch-oriented queries. So think of this thing. If you are using Apache Hive in your Hadoop cluster, which is a very possible scenario, to do any kind of querying on the data, and you are facing some high latency in your query execution, and you are planning to use Impala on top of the data that you have already in HDFS, because of its similarity in the metadata sharing, the same syntax it has, the same ODBC and the JDBC drivers, and also the same user interface, you will find yourself at home and will not have any steep learning curve implementing Impala if you're already implementing Hive. This is a very good thing, and it actually helps getting the data scientists or the data analyst aboard without any steep learning curve. Impala is an addition to the tools available for querying big data. As we have discussed that Impala do not use MapReduce at all, but please be noted that it does not replace the batch processing framework built on MapReduce such as Hive. Hive and Impala, they are completely different solutions fitting for different worlds altogether, and they have their own pros and cons. We'll discuss about these pros and cons later on as we move ahead in the slide. As we are discussing, Hive and other frameworks which are built on top of MapReduce are best suited for long-running batch jobs, such as those involving batch processing of extract, transform and load, popularly called as ETL type jobs. The reason that we choose Hive on Impala for such kind of long-running jobs is something which is to be discussed upon, and we'll take care of these things in the upcoming slides. As we have discussed that Impala actually supports a very wide variety of file formats, here is a slide which is dedicated to it, and we are going to discuss about what are the file formats supported by Impala. Impala supports the uncompressed as well as the LZO compressed text files. It has the support for sequence files and RC files with Snappy or gzip, where sequence files and RC file is the type of the file, and Snappy and gzip are the compression codecs which can be used on such kind of files. Impala also has the support for ORC files. It supports the Evrodata files, which is very popular due to its high compression rate, and also the metadata is stored separately so that it can be processed there. Also, the common man's choice in a big data ecosystem, which is Parquet, is also supported with Impala. In fact, Impala clubbed with Parquet gives you the best possible speed on your data which is stored on HDFS. Let's discuss about the SQL support that Impala provides. We have till the time discussed that Impala is pretty much similar to Hive and actually uses the same kind of SQL syntax. Essentially, neither Hive nor Impala are SQL 92 compliant, and they provide almost everything minus the correlated subqueries. Impala also provides you the option of using the insert into commands or select from this particular table command, and we can easily use these kind of queries to do transactional operations. As it is in the case of Hive, Impala also supports only equijoins and no non-equijoins are supported there. Also, due to the distributed nature of the data in the case of HDFS or S3 or any other file system which is used in big data ecosystem, cross products are also a strict no-no in Impala. The order by clause also require a limit. It has a very limited DDL support, so you can see that limited is something which is mentioned in brackets. Although user-defined functions and user-defined aggregate functions, which are commonly known as UDF, which stands for user-defined function, and UDAF, which stands for user-defined aggregate functions, are pretty well supported in Impala. Looking at all these slides, you may have that feeling that it is somehow very much correlated to Hive, and that is something that we have already discussed, that this is the biggest advantage, that if someone knows Hive and is actually already implementing that, without having much of the learning curve, he or she can directly jump onto using Impala in his or her cluster. Alright, after discussing a brief introduction about Impala, let's see that why Impala is beneficial and what are the use cases or the things which actually pushes the Impala as an advantageous tool against Hive. First of all, it has the familiar SQL interface that data scientists and analysts already know. This thing we have discussed a couple of times, that Impala is pretty much similar to Hive, which in turn is pretty much similar to any SQL dialect. So you can have that select star statements, you can have that insert statements, you can have the join statements, which is as it is used in other RDBMS engines, and so on. In short, as we have discussed in the previous slide, Impala is SQL 92 barring the correlated subqueries. Moving ahead, Impala has the ability to interactively query data on big data in Apache Hadoop. As we have discussed that if we are using Apache Hive to query our data which is stored on HDFS, we might see a bunch of seconds of delay, or you can say that startup time, to launch the map and reduce jobs. It actually kills the sole purpose of interactive queries and may sometimes be annoying to the end users. Impala, on the other hand, is pretty much interactive, do not have that cold start problem, and gives the results instantaneously, cutting short on the execution time since it do not need to initiate the MapReduce jobs. Impala distributes the queries in a cluster environment for convenient scaling and to make use of cost-effective commodity hardware. As we have already discussed, Impala is installed and can be configured and executed on the same cluster which is used for other different components of Hadoop ecosystem, and it will process the data which is stored on the HDFS of your Hadoop solution. As is the case with different MapReduce paradigm tools, for example Pig and Hive, Impala will also distribute its queries in a cluster environment, and it will help us parallelizing as well as scaling the problems that we have, or the data processing problems that we may have, and will give us faster resolution due to the distributed nature of work. Impala has the ability to share files between different components with no copy or export import step. For example, if I want to write with Pig and read with Impala, or to write with Impala and read with Hive, that is pretty much possible. In fact, Impala and Peg, because they actually create some metadata, have some tables, have some partitions or some indexes created, both of them, Impala and Hive, can share the same metadata store, and we'll discuss about this thing in detail in the upcoming slides. Also, a data which is written by Peg can be read very easily with Impala, because both these tools are going to use the Hadoop distributed file system to read the data as well as write the output that they are going to process upon. Impala is a single system for big data processing and analytics, so the customers can avoid costly modeling and ETL just for analytics. So in case you guys are actually picking up the data from the source, and you are actually processing a lot of things on top of that particular data, and you are getting that data to work upon different ETL stages, then loading it up, and at the end of the day you are using some tool to have the visualization on top of it. You can simply avoid it and can use Impala to actually process the data which is stored on HDFS, and you can have pretty quick results out of it. Because, as discussed earlier, no MapReduce job is going to be executed, and we are going to leverage the massive parallel processing query engine developed by Cloudera from grounds up to execute our real-time SQL interactive queries on the data stored on HDFS. Alright, after discussing about these bunch of benefits that Impala actually gave me, let's move ahead and see that how Impala is different than Hive. First of all, Impala is SQL on HDFS while Hive is SQL on Hadoop. Now this thing might be a bit misleading and might actually trouble you by understanding that what it actually means. First of all, let's discuss about Hive. The first bullet, it says that Hive is SQL on top of Hadoop. Now, let's break this Hadoop thing into its two core components. As we know that Hadoop is a collection of two things. First, a way to store the data. Second, a way to process the data. The way to store the data is commonly HDFS or Amazon S3. The way to process the data in Hadoop is commonly MapReduce. So when we say that Hive is SQL on Hadoop, so Hive will actually leverage the MapReduce processing paradigm, which is the way to process the data which is stored on HDFS, the Hadoop distributed file system. So whenever we are going to fire any SQLish kind of query using Hive, it will first be converted into MapReduce and will then be executed on the cluster to process the data which is there on HDFS. What it does, it actually adds this cold start problem where a bunch of seconds are used to initiate the MapReduce job. Impala, on the other hand, is SQL on HDFS. Now what does that mean? So if you are correlating it to the previous thing that I have discussed about that Hive is SQL on Hadoop, in this case we are talking only about HDFS and we are not leveraging anything related to MapReduce. So I will have some data which is stored on HDFS, and instead of using the MapReduce ecosystem to process the data, I will use my Impala engine, which will have some SQL queries written to process the data directly on HDFS. It will avoid the bunch of seconds which are there to the cold start to initiate the MapReduce jobs, and will actually save that time and will speed up my processing. Alright, moving ahead, Impala uses the MPP engine to distribute the query processing while Hive uses MapReduce. That is pretty much that we have discussed in the first bullet point. Let's discuss again that MPP is massive parallel processing engine developed by Cloudera, and MapReduce is something that you actually already know. There is no MapReduce overhead in case of Impala, while Hadoop, which actually use MR, has the overhead attached to it, and Hive is going to use this ecosystem. Hence, the queries which are going to be executed using Impala are going to be very fast in nature as compared to the queries which are going to be initiated by using Hive. There are a lot of benefits that we have discussed about using Impala, but Impala has its downside too. As it is discussed in the fourth bullet point, Impala is not fault tolerant while Hive has the usual fault tolerance of the MapReduce. Now what does that means is that although Impala is not going to use the MapReduce processing paradigm, it actually is going to use the similar kind of processing paradigm where it will actually process the data stored on HDFS and will distribute the load accordingly on the different nodes which are there in my cluster. Now, what happens in MapReduce when the data is distributed across different nodes and it is processed on different nodes across the cluster? If any of the node fails, the execution is triggered on some other node having a copy of this data. But in case of Impala, that is something that do not happens. For example, I have my query which is going to process a table employee, and the data for this table employee is stored on 10 different nodes. Now, when I'll trigger my query, I will have this query triggered on 10 different nodes to leverage the parallel processing paradigm. But assume if one of that particular node fails, Impala will not try to restart that particular node or reprocess that data somewhere else. Rather, the query will crash, or you can say that the query will append, and the user has to refire the query, hence leaving Impala with no fault tolerance at all. Hive, on the other hand, has the usual fault tolerance which is attached with MapReduce that we have discussed earlier. Okay, moving ahead, the MapReduce paradigm actually materializes all the intermediate results which enables better scalability and fault tolerance, but actually slow down the data processing at the same time because the data needs to be written to the disk is something which is not there in Impala. What Impala does is it streams the intermediate results between executors and makes the processing very fast. But the thing is, it actually trade-offs on the scalability. Also, Impala is recommended for real-time SQL queries while Hive is recommended for large batch jobs. The sole reason for that is because, as we have discussed, that Impala is not fault tolerant. Now say that you have very large data set to process and you are actually planning to do any kind of ETL on top of it. If we are going to use Impala and we are going to execute that job, now let's take this example that this job or this SQL query actually takes 4 hours to be processed. Now I have my data processing going on for 3.5 hours, and in the last half an hour a given particular node on Impala fails, is crashed, and actually according to Impala's architecture, it will not try to start that process again on the same or some other node. Hence, the user end up starting the query again from the scratch, and he actually needs to wait for 4 hours to get the results. On the other hand, if Hive is used in this particular case, even if the node fails, the job will be restarted or the task will be restarted on some other node which is having the replica of that particular block. Hence making it fault tolerant and not actually needing the programmer to restart the query again and actually waste the time, all the time that actually he was sitting there waiting for the results. On the other hand, Impala is pretty fast with real-time queries because I do not use MapReduce. Hence, it's the best candidate there, and even if my job fails or my query fails, I can easily restart it without worrying much about the time it is going to consume. Okay, Hive generates the query expression at the compile time, whereas Impala does the runtime code generation for big loops. Now, what is this? Whenever we write any Hive query, it is actually going to be converted to MapReduce. Now, because it is going to be converted to MapReduce, we actually first of all need to compile that code, convert it to MapReduce script, and then execute on the slave nodes. But in case of Impala, there is nothing like an intermediate thing which is called as MapReduce, and the same query is going to be scaled upon the parallel nodes which are there, and the processing will just happen. Okay, so that was a lot discussing about the differences between Impala and Hive. Let's move forward. Now we are going to discuss about the core components involved in Impala. Impala has three major components which are Impala daemon, the Impala state store, and the most important that you can say, the Impala metadata and the meta store which is going to have that metadata. In the diagram you can see that I have the HDFS data node, which is actually the storage layer, and on top of it, I have this Impala D, which is Impala daemon. I have this Impala D, which is Impala daemon, the query planner, the query coordinator, the query execution engine on top of this HDFS node where the data is stored. And it actually is interacting with the Hive metastore, the Impala state store, and the HDFS name node. Also, this Impala D is actually interacting with the command line interface, the third-party applications, SQL, or the ODBC and JDBC drivers. Also, Impala is present there on Apache Hive, and you can trigger it anytime from there and actually start writing your queries. Now, the purpose of displaying this diagram is to actually tell you that to the right hand side, the complete Impala execution engine, which actually involves query planner, the coordinator, and the execution engine, uses the same Hive metastore. Impala state store is a particular process that we will discuss about in a couple of minutes, right? HDFS name node is the master component from the Hadoop architecture that actually stores the metadata and tells where the data is. So looking at these three components, we can say that Impala actually pretty much utilizes all the components which are already present and are utilized by other tools and need not to implement any new thing there. Same is the story with the components which are there overhead, for example, the CLI, the SQL, the third-party applications, the ODBC and the JDBC drivers, or Apache Hive. That is something which was already present in our Hadoop ecosystem, and tools like Hive were already using it. So Impala is going to actually utilize all these things and is going to give us a pretty fast real-time execution engine kind of uh, tool to us. Now let's move ahead and discuss about these core components in detail. First of all, let's discuss about the Impala daemon. The Impala daemon is kind of a slave process and it runs on each data node where Impala is installed. Now, let's take example of the MapReduce processing paradigm. In MapReduce processing paradigm, slave nodes have two processes which were running on each and every slave node, which were data node and node manager. Similarly, Impala daemon or Impala D is the slave process which is running on each and every machine where Impala is installed and will take care of the distributive task which is going to be assigned to it. The Impala daemon is represented by an actual process name as we have discussed, and it is called Impala D, where Impala is the name of the tool and D stands for daemon. Impala D is responsible for processing the queries which are submitted through the Impala shell, the API, and the other third-party applications connected through Open Database Connectors or Java Database Connectors or Hive. Now, as we have discussed earlier, the queries can be executed using the shell, the application programming interface, or any other tool. Whenever this query will be executed, it will be distributed to different data nodes or Impala Ds, if I may say that, which are going to execute the query in parallel and going to give us the results. Parallel processing makes the overall execution time reduced by a lot, and Impala D is the slave node which is responsible for taking up that query and process it in parallel. Now we are going to have Impala D running on each and every slave node. So if I discuss about a sample cluster of 10 nodes where Impala is configured, I'm going to have 10 Impala D processes or services running there. As it happens, whenever I have a query, it can be submitted to any Impala D running on any node. Now, when the query is submitted to any of the Impala D node, right, or any of the Impala D process, which actually can be present on any of the slave machine, it's not necessary that the same slave machine will have the data which is supposed to be processed. Now what happens is that particular node which actually receives the SQL query acts as the coordinator node for that query. It then actually initiates multiple queries on different nodes which are supposed to handle the data supposed to be processed by this particular SQL query. Now once the Impala D accepts the query, it reads and writes to the data files and parallelize the queries by distributing the work to other Impala nodes in the Impala cluster. Now, when the data, or you can say that the query is distributed to the nodes which are having the data, they will process all the data in parallel, and when the queries are processing on various Impala D instances, all Impala D instances return the results to the central coordinator node. Depending on your requirement, queries can be submitted to a dedicated Impala D or in a load balanced manner to another Impala D in your cluster. Now there is a diagram which is actually going to help us here. Now let's take this example that I am going to have a particular query which is going to be executed from either the Impala shell or the JDBC and the ODBC client. In that case, say this central Impala D process is going to act as the coordinator node. Now, when this node is the coordinator node, the Impala shell or the JDBC client will actually sends the query to this node. This node in turn will start executing the query on different nodes which are supposed to actually have the data stored for that particular query. Take an example that the node to the left and to the right are having the data instance stored there. This middle Impala D process or this middle data node or the slave machine will trigger that query on these Impala D daemons and will start processing the data in parallel. Once the left and the right Impala D processes or daemons are done with processing the data, they will return the data back to this centralized Impala D node, and it in turn will return the data to the client whosoever it has asked for. For example, Impala shell or JDBC ODBC client. That is how an Impala cluster works, and that is what the role of Impala daemon is. So just to cover it up in a nutshell, Impala D is a process which is running on each and every slave node, and each and every slave node can actually receive the query from any of the client, which can be Impala shell, third-party API, JDBC ODBC clients, or Hive. This centralized coordinator node is then going to distribute the query or the workload onto different other nodes and will actually collate the results from them before sending it back to the client. Alright, let's move ahead and discuss about the second process, which is called as Impala State Store. Impala State Store is responsible for checking the health of each Impala D. State Store takes the status of the health of each Impala D and then relays each Impala daemon health to other daemons frequently. So this is kind of a gossip protocol which is implemented there. So if I have 10 nodes in my Impala cluster, right, a state store process will actually have the status from each Impala D node from all these 10 cluster and will also send the status of other 9 Impala nodes or the Impala D processes to other machines. Now why this is important? As we have discussed that any node in Impala cluster can act as the coordinator node. The query can be submitted to this coordinator node on a round robin or a random fashion. This node is actually going to then distribute the workload onto different nodes having the data. Now if a node has the status of the other given nodes, it can actually choose the nodes wisely and it will not choose those nodes which are down, hence actually enhancing the query performance. Impala State Store is a single running process as opposed to Impala D, which runs on each and every node and can run on the same node where the Impala server or any other node within the cluster is running. The name of the Impala state store daemon process is called state store D. State store is the name of the process and D stands for daemon and hence the name state store D. Every Impala daemon process interacts with the Impala state store process and provides its latest health status, and this information is relayed within the cluster to each and every Impala daemon so that they can make correct decision before distributing the queries to specific Impala D. In any event where a node is failed due to any given reason, it may be some network congestion, it may be some hardware failure or so on, the state store D updates all other nodes about the failure. And once such a notification is available to all the Impala D, no other Impala daemon assigns any further query to the affected node. Thinking about that Impala, so the state store node or the state store D process actually helps the complete Impala cluster to take the decisions wisely that where the query should be executed and which node should be actually taken out of the processing. And it actually is very important as well, because taking this thing in mind that if any of the given node which is processing the query fails, the complete query will be marked as a failed query and the end user actually has to restart the query again. Hence, not choosing a bad node is very important in Impala cluster, and state store helps the query which is going to be submitted take the wise decision of which node to pick up and start the processing with. The state store component provides a critical update on the node in the trouble. The process itself is not critical to the Impala execution, however. Now, what does that mean? In an event where the Impala state store becomes unavailable, the rest of the nodes continues to work as usual. When state store is offline, the cluster becomes less robust, but actually do not stop working. And when the state store is back online, it restarts communicating with each node and resumes its natural process. So let's understand these 3 points in detail by looking at this diagram, which is actually shown in the bottom half of the slide. Alright, so the things that we need to take care in this particular slide is that I have 3 slave nodes where Impala D is running. So they are the bottom 3 lingering nodes which are actually connected to this unified metadata node, which actually has the state store D daemon running there. Now what this state store D daemon does, it actually coordinates with all the 3 Impala D nodes. It takes up the status from the first Impala D node and actually relays the status of this Impala D node to the other 2 nodes, and do this thing or this kind of processing with other nodes which are present in the node in the cluster as well. Now what it does, that every Impala D node in this particular case knows about the other Impala D nodes in the cluster. So if any of the Impala D node is going to act as the coordinator node, it will take care of this thing that the default or the defaulters or the bad Impala D nodes which are down should not be taken into picture. Now this state store is providing very critical update to the Impala D nodes. Understood? But what if this state store D process actually crashes out or it fails? Does it makes the state store D as the single point of failure for my Impala cluster? Well, essentially no. The biggest impact that we will get if the state store D cluster is crashed, that these Impala D nodes will no longer be able to interact with each other to have the status relayed, and hence they will not have the up-to-date status of the other D Impala D nodes in the cluster. What does that mean? That it will make my cluster less robust. Whenever any of the Impala D node is going to act as the coordinator node, and it will not have the up-to-date status that which of the other 2 nodes should be left off or which of the nodes should be taken into account to do the processing, and it will actually essentially try to start the processing on the node which is down, and hence will affect the availability or the overall robustness of the cluster, and it may result in a couple of SQL queries which are fired to fail. But as soon as the state store D process is brought up back again, it starts its usual processing, that is communicating with the Impala D processors in the cluster and relaying the status to the other Impala D nodes, hence resuming the robustness of the cluster back. Alright, so just to summarize in a nutshell what state store is, it is a centralized process which actually connects with all the slave Impala D nodes and relays the status of one Impala D node to the other Impala D nodes in the cluster. And hence it does the same for all the Impala D nodes and make sure that every Impala D node is aware of the status of the other n-1 Impala D nodes in the cluster, which actually helps us to make a wise or more robust decision as far as the query execution is concerned. Moving on, we'll discuss about a critical component which is Impala metadata and Impala metastore. Impala uses traditional MySQL or PostgreSQL databases to store the table definitions. This is the same kind of solutions that Hive also implements. While other databases can also be used to configure the Hive metastore, but MySQL or PostgreSQL are most widely used and are widely recommended to be used as a metastore. The important details such as the table and the column information and the table definitions are stored in a centralized database which is called as a metastore. Apache Hive shares the same databases for its metastore, because of which Impala can access the tables which are created or loaded by Hive if all the table columns use the supported data types and data formats that are actually supported by Apache Impala. Same is the case with the compression types which are there in Impala and Hive. If they are compatible, they actually can be shared across the tools, and a table which is created in Hive can be used by the table created in Impala, and a table which is created in Impala can be used by the Hive ecosystem. This nice gesture of metadata sharing helps the end user a lot, and it actually prevents the creation of the same table information at two different places, and hence saves a lot of processing time, also saving upon a lot of mess, allowing the end user to actually switch between Impala and Hive as and when necessary. Besides that, Impala also maintains the information about the data files which are stored on HDFS. It tracks the information about the file metadata, which is the physical location of the blocks about the data files in HDFS, and it actually helps the query to locate the data whenever it is fired. The benefit of having the metadata and the block information cached is that Impala can easily bypass the need to look up those things and can hence actually provide you the real-time query feel without actually wasting the overhead time in looking up for these things. Each Impala node caches all the metadata locally, as I was discussing in the previous bullet, which can actually expedite the process of gathering the metadata for a large amount of data which is distributed across multiple data nodes. When dealing with an extremely large amount of data which actually cannot be cached locally, or many partitions which are again very difficult to you know uh, to be placed on a single machine or to be taken care as locally, getting the table specific metadata could take a significant amount of time. So a locally stored metadata cache helps in providing such information instantly. So Impala, what it does, it keeps the information of the metadata as well as the block cache, which actually helps us bypassing the lookup into the name node and start the processing as soon as possible. To actually summarize this thing in nutshell, Hive and Impala shares the same metadata and can actually share the tables which are created in one tool can be utilized in the second tool. That is, a table created in Hive can be used in Impala, and a table created in Impala can be used in Hive. They can also leverage the table definitions, and the tables can be processed given that the column types or the data types of the columns are compatible and the compression types used, if any, are also compatible. Impala also caches the metadata locally, which actually helps it preventing a lookup onto the centralized data store, metadata store, whenever a query is fired. Also, Impala caches the metadata or the block cache, uh, and whenever a particular file is supposed to be processed using any SQL query, instead of going back, looking into the name node and picking up the metadata from there and wasting some time, Impala can actually fetch the locally cached metadata or the block cache and can start the processing as soon as possible. This helps prevent an extra round trip and actually prevents the overhead to get the metadata and then start the processing. Okay, so we have discussed about various aspects of Impala, the benefits, the advantages, uh, its difference as compared to Hive, the Impala D processors, the state store, and the meta store. Now, what if we have Impala installed and we want to start the services of Impala? We can use the impala-state-store command to start the state store D process. State store D process, as we have already discussed, is very advantageous in actually picking up the information, the health of all the Impala D processes and relaying it to other n-1 Impala D processes running on the cluster. Similarly, to start the Impala D process on each data node, we can use impala-server command, and we can actually pass the start option with this command to start the services. Also, please be noted that Impala state store and Impala server specific initialization scripts are located under etc default /impala. So that is the folder where you have configured Impala. Inside that, you will go to /etc. Inside etc, you will find a folder called default, and inside default, you are going to have a folder called Impala, and inside that, you are going to have these scripts that you can actually use to initiate the state store D and Impala D daemons on my Hadoop cluster or on my Impala cluster, sorry. Similarly, I can use the aforementioned scripts to stop the Impala services as well. So simply replace the start with stop in case of Impala state store script, and it will stop the state store D daemon. Same case goes with the Impala server, and if we use Impala-server space stop, it will actually stop the services which are running across the different nodes on my Impala cluster. Similarly, using the restart passphrase at the end of these scripts, I can restart the services on my Impala cluster. These things are very important when we are actually working on an actual cluster, and for one or the other reason we may need to stop or restart the Impala processes which are running on the cluster. Alright, moving ahead, and also please be noted that the stop and the restart options can be done from the same folder, which is /etc/default/impala, and inside that you are going to have impala-state-store as well as impala-server, where you can use different options like start, stop, and restart to do the appropriate actions. Okay, let's move ahead and discuss about the Impala execution engine. First of all, let's take up the query execution phase. Let's say the request for processing this particular query is arriving via ODBC or the JDBC connectors. The Impala planner turns the request into a collection of plan fragments which are actually then sent to the coordinator, which initiates the execution on remote Impala Ds. Please be noted that any of the given Impala D is going to act as the coordinator node as it has been discussed earlier, and this coordinator Impala D node is going to start the execution on remote Impala D processes which are running on the slave machines. During the execution, the intermediate results are streamed between executors. That is, they are not stored on the disk, but are rather shifted to the coordinator node. The query results, after being collated or collected from different executors, are then streamed back to the client. Subject to the limitations which are imposed on the results, for example top n aggregation, the results are filtered and are then presented to the end user. The diagrammatic representation of the execution engine will goes like this. For example, I have a SQL app or an ODBC connector which actually sends a SQL request to be executed on the Impala cluster. In this case, the three blocks that I can see in the bottommost layer are the three different nodes in my Impala cluster. Any of this node is going to take up the request and is going to act as the coordinator node. In this diagram, you can see that the node which is in the middle and whose query planner is colored red is going to act as the coordinator node and is going to take the SQL request. This coordinator node has the information about other Impala D daemons which are there in the cluster, and it will actually spawn the processors there on these different machines to start the SQL processing. So this query coordinator started the processing on the slave machine which is on the left. So the query coordinator will actually start the processing on the query executors of these three different nodes, which is the query executor of itself and the query executor of the Impala D daemons running on the left and the right hand side, and the execution will start parallelly. Moving ahead, once the execution is done, the query executors will actually collate the results and will send to the query coordinator of the centralized or the coordinator node. This coordinator node, after having the results back from all the query executors, will send the query results back to the requesting client. We discussed that Hive and Impala shares the metadata across themselves. So one of the RDBMS engine, for example MySQL or PostgreSQL, will be used to actually store the metadata. It can be the table definitions, the columns, the create table parameters, which actually confines as the logical metadata. And for Impala, it's not only the table definitions, but also the HDFS name nodes, directory contents, and the block replica locations. This actually helps Impala to have these information cached. Apart from the Hive metastore, it actually also caches the directory content, the block replica locations, and also the block replicas volume IDs, so that whenever it is required, instead of going back and looking onto the name node, it can actually directly jump onto these nodes and start the processing there. So Impala has three different categories of metadata. First of all, it is having the local copy of the Hive's metastore, which is actually the logical metadata, including the table definition, the columns, and the create table parameters. Second, it has the HDFS name nodes metadata, which is directories content and the block replica locations. And third, whatever replicas have been created, the volume IDs for those replicas are there with Impala. Impala, as discussed earlier, it caches the metadata. So there is no synchronous metastore API calls during the query execution. That is, for example, if Hive is storing the metadata on MySQL, Impala will not go to MySQL instance running, which is having the metadata, each and every time a query is executed. Instead, it will actually caches the copy of the metadata with its executor nodes, and it picks up the metadata from those nodes as and when required. It actually saves a round trip problem for Impala execution engine to the metastore. The Impala instance reads the metadata from the metastore at the startup and actually keeps a local copy. Catalog service relays the metadata when you run the DDL or update metadata on one of the Impala process. Also, we have a bunch of commands which are available, for example, refresh or invalidate metadata. Now, the refresh does reloading of the metadata on all Impala Ds if we add a new file via Hive. That is, we discussed that Impala is going to have three different kinds of metadata. First of which was the logical metadata, and the second of which is the HDFS name node metadata being, and third was the block IDs. So whenever we are going to add a new file, it means we are actually pointing to some new blocks on HDFS, mapping of which is stored on the HDFS name node. Now, because Impala has done a caching of that particular information, means that Impala will keep on using the stale metadata information of HDFS name node until and unless it is updated on the slave nodes or the Impala daemons of the Impala cluster. So how to do that? The refresh command actually does the purpose for us. It picks up the metadata from HDFS name node and gives the updated metadata to the Impala D processes, hence making it easy to have the updated information and do not miss on any data which is provided. Similar command which is available is invalidate metadata. What it does, whenever there is a new table which is created on Hive, and if you go ahead and try to use that table in Impala, you'll see that that table is not listed there on Impala side. The reason for that, because Impala actually caches the metadata and hence leaves little room for addition of any metadata addition on the runtime. Invalidate metadata is mandatory after you create a table on Hive side and want to use it on the Impala side. Whenever we will use the invalidate metadata command, it will pick up the metadata from the centralized MySQL or whatever PostgreSQL metastore, and it will update the metadata on all the slave nodes or the Impala D daemons which are running on the data nodes of the Impala cluster, hence making sure that all the newly created tables are actually reflected on Impala and the drop tables are no longer there in the metastore of Impala daemons, hence making sure that up to date metastore is replicated on all these nodes. However, please be noted that invalidate metadata and refresh commands are necessary whenever the changes are made on the Hive side, because Impala tends to cache them. In case you create a table on Impala side or you add a new file on the Impala side, you need not to use these commands or you need not to worry about updating the metadata on Hive side, because Hive all the time goes to the centralized metastore, which may be in MySQL or PostgreSQL or any other RDBMS engine, to get the logical metadata, and it always goes to the name node to get the block replication information and volume IDs for the replicas for the blocks which are created, hence having accessing all the up-to-date information regarding metadata for every execution. The bad side, Hive actually will have a significant overhead looking for these metadata each and every time. A good side, Hive need not to actually refresh these informations and need not to worry about that if the developer mistakenly forget about using refresh or invalidate metadata, that he or she will keep on using the stale data there. So if we actually brief it up again, Impala and Hive uses the same metadata, with Impala storing a bunch of other information alongside logical metadata, which is actually the HDFS name node metadata, which essentially is the block information and the volume IDs of the replicas created for those blocks. The logical plan or the logical metadata is updated on Impala side by using invalidate metadata command, while the HDFS name node information is updated on Impala side by the refresh table command. These commands are not required on Hive side. So before we wind up, let's have a quick recap on what we have covered in this session. We went through a brief introduction about Impala. We discussed about the advantages of Impala. We discussed that how Impala and Hive are different from each other. We take out a couple of pages from our slide discussing about the core components of Impala. We also discuss about the execution engine, and in the end we discuss about the metadata caching, which actually is accomplished by using invalidate metadata command to actually cache the fresh logical metadata from the metastore, and using the refresh command to actually update the block caching of the HDFS name node and also the volume IDs of the replicas created for those blocks. With this, I conclude this session on Impala. Thank you and have a nice day.